This question is quite the boss. You have a spherical planet with certain mass and radius. Planet is assumed to be in space by itself and has all the mass concentrated at the center. Now this planet spins on its axis with angular speed. You see this arrow here that shows you how it's spinning, like our Earth. And got a pose there. Anyway, a small object of mass m rests on the equator. So here's one little fella. Surface of the planet exerts a normal reaction force. Normal reaction force means if you have a surface like this, and you're in contact with the surface will push you up. If you are this sphere, push you up at right angle from the surface. So that's what we call N, normal reaction force. State the formula in terms of m, and r for gravitational force between planet and object. This is very important. It's between planet and object. Means I don't care where you are on this planet. You could be up here. You could be any of those dots. You will have the same gravitational force pulling you towards the center of the planet. 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 This is all Fg. So what's the equation for Fg? This will be Gmm over... What's the radius? Radius of the planet is, we assume, to be fixed, so big R square. The second one, formula for centripetal force required for circular motion of the small mass. Now, this one is a bit more tricky. You need in terms of omega, right? Omega means you have to use the mr omega square. But is this R going to be big R as well? It really depends. Because you see, let's say we draw another planet here to show the centripetal force. Okay, if I am at the equator here, I am going to rotate in this direction around the planet. Right? So my orbit radius R is going to be from here to here. That's R. So yeah, if you're at the equator, both R's are the same. So let's write it down first. So instead of small r, I'm going to write big R. Big R omega. So this one is 2 marks. 1, 2. B1, B1. But before we go to the next part, here's a question. This is only if you're at the equator, then the R's are the same. The purple color R radius to center of the Earth is the same as your orbit radius R. But if you move away from the center, okay, let's say this is position 1. Now you move to position 2 up here. Now it's a little bit different. At position 2, your orbit radius is now a bit smaller. You're going to go around the planet like this. So this is definitely not R anymore. This is some R that has decreased to be smaller. But it's not R because big R is from you to the center of the planet. This is big R. And that is not your orbit radius. So just keep in mind, this is orbit radius. This thing. Okay. Alright, with this in mind, let's go on to the next part and see what are they asking. Okay, so we need another equation for normal reaction exerted by planet on the mass. What's our normal reaction again? Okay, let's go down and see. Okay, I'm going to rub off these pictures and draw the forces at work. Okay, let's assume we're at the equator first. Nice and easy at the equator. So we have a particle or mass, whoever it is, on the surface. We have what forces acting on it again? The first one is going to be gravitational force towards the center. We call this Fg. And we have a normal force. What shall we call it? Green color. Okay, normal force that will push this mass outwards. Something like that. Let's just draw it like this. Okay, this is called N. And both of these forces will contribute to centripetal force, which is towards the center. I put bracket, the net force towards the center of the Earth. So what is that net force? We can write out at the equator, this will be, let's use blue color. Okay. Fc, net force Fc equals to, who is pointing to the center? Fg, right? So this is a positive. Who is pointing away from the center? You give negative. Remember the circular motion videos that we looked at earlier? Okay, so this will be Fg, a positive, minus N, that is pointing away. So that will be your centripetal force that will actually keep you going in a nice circle around the Earth. So let's take this equation up there and continue to use it. Fc equals to Fg minus n. Right. So here. Okay, so Fc, right here. Fc equals to Fg minus n. Ooh, some weird jumping is happening on my OneNote. Fc here will be our mr omega square, which we looked at earlier. Fg is going to be gmm over r square minus n. So we rearrange all these for n equals to some equation. Then you will have n. Actually, we should rearrange first, right? What am I doing? N equals to Fg minus Fc. Let's just write that down. Okay. So Fg will be always gmm over r no matter where you are in the planet. R square, sorry. Minus centripetal force. Now, if you are at the equator, then you can say mr, big R, omega square. This is true only at your equator. Okay, so this is how I can write the equation for our centripetal force, gmm mr omega, only equator. The other one, by the way, I should circle it. This R is everywhere on the planet. It's the same because the planet is a sphere, right? The radius is always the radius no matter where you are on the planet. So here comes the tricky part on part B. Explain why the normal reaction on the mass have different values when you're at the equator versus when you're at the poles. Let's go back to the picture and see. Why is normal reaction different in the first place? Well, you see, when you are at the equator, you have this value, right? If you are at the pole, let's say the North Pole, I put a little dot there. You have Fg pulling you down, yes. You have normal contact force, yes. Let's put it normal contact force. But do you have any kind of circular motion happening? No. You are just up there on the pole, everything is spinning around you. There is no rotation when you are at this position. So, no rotation. You are not moving in a circular path. When you're at the equator, you are moving around like this. You go further, you go higher up, you're moving around like this. You're at the top, you're just... There is no orbit radius. No orbit radius, no circular path. So, you want to write the equation, it will be something like this. C equals to Fg minus n. Yeah, we keep this first. Or we can rearrange this to be in such a way because there is no rotation. Mr omega square equals to Fg, which is the same everywhere, minus n. Radius is 0. Orbit radius is 0. So this whole thing is gone. So what you have is, just as if you are standing on a stationary object, Fg equals to n. Or I could rearrange it and say n equals to Fg. Whereas down there, you have n equals to Fg minus the centripetal term for centripetal force. See the difference? So which one do you think have a larger normal force? Of course, this one lah. There's nothing to minus the Fg ma, so your Fg is your normal force. Whereas if you're at the equator, Fg minus this centripetal force, the term, is kind of like it swings you out a bit, so you feel lighter. So actually it's very interesting. At the poles, n is actually what the weighing scale measures, this n. So if you set on the scale, you actually be lighter. Be heavier. You are heavier at the pole. So weird. Then if you are at the equator, you are a bit lighter. You're like, hey, I lose weight. No. It's just physics at work. You are lighter at the equator. This is so weird. Why? Well, it's the physics of circular motion. Okay? So there's no Fc. No rotation, no orbit, no Fc. Nothing. All 0. So how do we describe the changes? What is changing? The orbit radius is changing. So let's write it out. What happens when you are... Why is there a different value of normal reaction? You can say as as a mass moves away from equator, okay, move away from equator, then what changes? The r orbit radius, let's call this r, in the term mr omega square, is for centripetal force, decreases. Smaller and smaller orbit radius, right? Okay, so what does that mean for our normal radiation force? Or you can say decreases or varies lah. Varies also can as a acceptable masking answer. So as you move further away, your mr omega becomes smaller, can even decrease to 0. So the normal reaction force increases. Alright, so one idea the mark scheme is looking for is your understanding that the mr omega, this term is changing or varying or decreasing. Okay, the idea is changing lah. So you got to talk about the r in the orbit radius, r in mr omega. That's the first point. The second point is that it becomes smaller, so decreases, or you say to 0. Also can as you go closer and closer to the pole. All the marks is there. No mark for normal radiation force. Okay, never mind. Another possible answer to add in is another method, is to talk about this. You can say, in terms of vectors, that your mr omega square is not parallel to the gravitational force anymore. Or you can say not perpendicular to the surface anymore. What does that mean? Time to do more drawings. Okay, let's go back to the planet. Okay, how does that mean? So we look at equator and at pole. What about in between? What if we were somewhere in between? Can we make an equation for it? Maybe, maybe not. So let's say we are somewhere at this latitude. Somewhere here. There we go. You have a gravitational force, yes, pulling you to the center of the Earth. But that is not the force exactly that is giving you your orbit radius. Remember, you're orbiting like this. You're orbiting in a circle, but the force is pulling you downwards. So there's some kind of weird resolving of forces that you need to do. There is N, which is perpendicular to the surface. But you need a centripetal force, which is all the forces resolve in this direction towards the center of your circular path. Wow! This is your centripetal force when you are at this position. Because you're going in a circle like this. So, cannot already lah. You see all these things not parallel. Centripetal force is here. You have to resolve all these forces. What a mess. That is geophysics. Okay, we'll leave it to that. But this is what you need to know lah. So remember, especially for questions that you are on the surface of a rotating planet, be very careful what the R you are talking about in your equations. This is a nice simulation that kind of shows, if you find it hard to imagine what's going on. This is our planet Earth with some countries on the list. Australia, Singapore, Oslo. And all these places, the gravitational force, assuming it's a perfect sphere, gravitational force is the same. But your orbit radius is different. Can I make this more transparent? Oh, I can. Let's take this out. So we can see, different slices. You see Singapore is at the equator and you have a pretty big radius as you go around the axis of the Earth. So you need a really big centripetal force. Oslo up here near the pole is a very small radius. Smaller centripetal force term. Melbourne somewhere in between. South Pole, look at this South Pole. If you are at the South Pole, there is no orbit. You are just there, spinning on the spot, but you're not going in the orbit around the axis. So keep that in mind as we go on with this question lah, okay? So if you ever get to go to towards the North Pole closer, and you step on a weighing scale, don't get too happy and say, "Oh yes, I have lost weight." Or you go towards the equator and you're like, "Oh, I have lost weight." Physics. It's just a physics. Some force, funny, weird force stuff. You didn't actually lose weight. It's just the forces. The planet is spinning. And there's that. So let's move on. Part 2, the radius of the planet. This is all calculation here already. R is complete one revolution in this amount of time. Let's call this a period. Calculate the magnitude of centripetal acceleration at the equator. Okay, so we got to do A equals to... There's two possible choices. We could do V squared over R, or we could do R omega squared. It looks like we got to use the second one. They didn't give us anything about speed, so we'll stick with R omega squared. So A equals to R omega squared. Start off by writing the equation. Then write your thing here. So this is 6.4 times 10 to the 6 meters. Omega is 2 pi over t. So 2 pi over the time, 8.6 times 10 to the 4 square. Okay, so this one would give you a value, if you press calculator correctly, 0.0342. So we could keep, I guess, 2SF, 0.034 as our acceleration when you are at the equator. This is A1. You substitute the correct values in. That's another one, C1. Now the next part wants to troll you. So this is centripetal acceleration at the equator. Why? Because remember, we have a planet, right? Planet is like this. We are at the equator. And we are going in a circle. So there is centripetal acceleration that keeps us going in a circle. But now you are at the poles. Are you even rotating at all? Are you? This is our planet. Wait. Whoops. Click the wrong button. Let's zoom out a bit more. This is our planet. Oh no, it's out of shape planet. You are at the top. But the planet is rotating like this. How are you going to rotate? Just spin on the spot? Yeah. There is no orbit path. So, there is no circular motion. There is circular rotation, if you want to think about it. No circular motion or circular path. Hence, well, A equals to R omega square. Your R is already 0. Okay, so this orbit radius is 0. I'm going to write here a reminder. Orbit radius. This. Because you are here, what orbit radius is there? There's don't have. You're not moving in a circle. Whereas previously at equator, yeah, you move in a circle. Look at that big orbit radius. Now you don't. So it's just 0. Doesn't care what omega is. Just 0. Just write 0. So 0. So your answer? 0. There's only 1 mark to write a 0. So here's 1 mark. So make sure you know where are you? Equator or pole? That it does make a difference. Normal reaction force, orbit radius. You're just spinning on the spot. Go click on that simulation down in the link below, the one I showed you just now. Stare at it until it makes sense. Draw some vector diagrams until it makes sense. Okay, last part. It's a long question, my. Suggest 2 factors that could, in the case of a real planet, cause variation of acceleration in freefall at its surface. So now we're thinking of real life planet. Why is acceleration of freefall different? That's the A. So just now we already thought of the effect of circular motion. At the pole, there's no circular motion. I mean, no centripetal acceleration. It's AC. Now we're talking about other factors that can affect acceleration itself. So acceleration of freefall, you call it G. A equal to G. Assuming there's no other forces. What else could cause variations of acceleration? How do you find acceleration again? Newton's first law, F equals to ma, right? For any mass. What if you are in a planet, a spherical planet, we assume it's a sphere. This would be gmm over r square equals to ma. So your acceleration here is affected by the mass of the planet your own mass doesn't really matter because this cancels out. Let's just rewrite the whole thing. Never mind, I need to rewrite, I'm lazy. So you are affected by the mass of the planet itself or the radius of the planet. You assumed it was a perfect sphere. What if it's slightly stretched like an egg? What if it's bumpy and there's suddenly Mount Everest up here and there's a valley? Then your acceleration is not going to be 9.81 or whatever that is anymore. It's going to be different. So let's talk about these differences. Firstly, the radius of the planet is not constant. It varies. In real life, there is mountain, there is valley, so your acceleration of free fall is different. So you can write here lah, mountain, valley. So 9.81 is kind of we chose it to be 9.81, but it's not actually 9.81 everywhere. Number 2, sure, let's write out more answers. What else can we affect? Mass. So radius can affect acceleration. Mass of the planet itself can affect acceleration. So mass of the planet, the more proper term is to say the density. Density of planet is not constant everywhere because the material of the earth is different. Maybe in the part of the planet there's a lot of water, so there's lakes here. Then in some other part is a lot of grass, so here's a lot of green color, maybe some dirt, the density of dirt. Then in some part of the planet there's like an iron ore, so it's like super dense over here. Maybe here got some stone, so you see everywhere, it depends on what's in the earth, the density can change. What else can we add here? The last two is the effect that we talked about, the planet spinning effect. So depends on how fast the planet's if the earth slow down and start to spin, or depending on where you are at the pole or equator like we talked about, that's what we call the spinning effect. Spinning effect. Circular motion. Number 4, last one. We assume in this case that there is an isolated planet, but in real life we actually have a friend called the moon. You know, a tiny moon that dances with us, goes around us. That moon actually pulls on us, exerts gravitational force. We pull the moon pulls us, right? So you also have the effect of a nearby moon. Effect of a nearby moon. If you want to be extra and say, nah, but then we got Mars, we got the Sun, we got the Jupiter. Yes, they also have a force that they exert on us, but it's small. The moon is our nearest friend, so the biggest neighbor. So any of these choices, as long as you mention 2, you get a B2 mark for 2 points. Okay? So, that's all for this video. Go and relook at some of the earlier ideas, especially the spinning part, where there are 2 different radius, orbit radius and separation distance. Go check those out, understand a little better. But that's all for this video. I'll see you in the next one.